All right, so here I've got a practical question that we want to talk about. And you're welcome to pause this if you like, if you need to read through that, if you're taking notes from writing it down. So what we're trying to do here is we're talking about a wedding reception, and the wedding hall has two different kinds of tables. We have lots of information about them. We know how big they are, we know how much they cost, we know how many of them the facility has, and what we're trying to do is we're trying to minimize the cost. Okay, well, good. Here's let's start with our variables. I'm going to R equal the number of rectangular tables. And okay, now I'm a little stuck. I can't use R again for the round one, so let's use C. Right, C will be the number of circular tables. Okay, so what do I know? I'm trying to minimize the cost, right? And I'm given those costs right up front here. It's $28 for a rectangular table, so that's 28R, plus $52 for a circular table, so that's 52C, and that is my total cost. I'm going to go ahead and use a capital C for that. We're not going to have a lot of, it's not going to create a lot of confusion. Remember, we're really only going to refer to this cost function at the very end when we're substituting values into it, trying to find which one is the optimal combination of table types. All right, so what else do we know? Well, let's see. Just kind of start reading through here. Kathleen would like to rent the hall for a wedding banquet and these tables for 250 people. Okay, well, if I have R rectangular tables and C circular tables, how many seats do I have? Well, there's 6 per rectangular table, so that's 6R. And there's 10 per round table, so that's 10C. And this has to be greater than or equal to 250, not equals, right? Don't put equals in there. There may not even be a solution if you put equals. Equals assumes that the tables have to be full. And that's not the case. If the optimal solution fills up all the rectangular tables and gives me a partially full circular one, I'm going to be fine with that. Okay, so what else? Well, first, put the obvious in here, right? R has to be greater than or equal to 0, and C has to be greater than or equal to 0, because we can't have a negative number of tables. And what else do we know? The room has to have the room has a maximum of 35 round. So C has to be less than or equal to 35, and a maximum of 15. So 15 rectangular. So R has to be less than or equal to 15, and that's it. I've used, you can cross stuff off here if you like, right? I've used this 250 table requirement. I've used the maximum number of each type of table. And I used the table size, and I used the cost. So, excellent. There's my system of linear inequalities and my cost function, or my objective function. All right, so what's the next step? Well, this is going to start to get a little crowded because there's quite a few steps here. So I'm going to go to the next slide here. And I've eliminated the question because we're really kind of done with the question itself. All of the information, all of the relevant information from the question has been condensed into our system of inequalities and the objective function, which we don't need for this step, which is why I haven't included it here. What we need to do now is graph this and find that solution region. All right, so we know our answers have to be greater. Oh, sorry. Before we go any further, because this has a lot of potential for confusion. Since we're not using x's and y's, right? Since we're not using x's and y's, label your axes. This is going to be the C axis, and this is going to be the R axis. It's easy to get them mixed up once we get into graphing and trying to find coordinates and so forth. All right, so I know both of these have to be greater than 0. So as usual, right, we're just looking at values in the first quadrant. Now I also know C is less than or equal to 35. Okay, 35 is a big honking number, and I only have out to about 8 grid lines here. So what I'm going to do is I'm going to let one grid line be 5 tables, right? And I'm going to just kind of put a 5 over here, just as a reminder. We're going to do the same thing on both axes to keep everything in scale. All right. So now what are we talking about? C is less than or equal to 35. Well, I'm going to count out 5, 10, 15, 20, 25, 30, 35. That's right here. And we need less than that many. All right, and then I'm going to do the same thing with R, right? R has to be less than or equal to 15, so that's going to be 3 lines up. That's here. And we need less than that number, so that's good. Okay, so we're going on this rectangle so far. All right, now how about the diagonal line here? This will be 6R plus 10C equals 250, and R is in the y-axis position, if you will. So I'm going to solve this for R. 6R equals negative 10C plus 250. So R is negative 10/6C plus 250 over 6. And what does this come out to? Well, this is R is negative 5/3 C if I just reduce the fraction. And I'm going to have to graph this 256, so I'm going to make this into a decimal. This comes out to plus 41.7. Okay, so remember that we're counting by 5s, yes? So 41.7 is just a little over 8. So we're about 1, 2, 3, 4, 5, 6, 7, 8. I'm sorry, it's a little over 8, right? So let me go just a little bit higher than that. There we go. Okay, and now I really need to be careful, because is this going to cut off this way, right? So it intercepts somewhere down here. Is it going to go down here and cut across the corner here? I really need to be precise about where this lands. So what I'm going to do is I'm going to find the x. I'm going to go ahead and find the x-intercept of this thing, because that's really going to answer my question. Is the x-intercept over here on this side, or is it over here on the right side? All right, so if I do that, sorry, I'm talking about the x-intercept, aren't I? What I mean is the c-intercept. Right, so if I put 0 in here for R, 0 equals negative 5/3 C plus 41.7. Move the 41.7 over, minus 41.7 equals negative 5/3 C. So C is equal to 25. Again, I'm doing this with my calculator, right? So my calculator had 41.666666, right? And it remembered that was really 2/3. Okay, and that's why it gifted me with a integer answer here. All right, so where is this? Well, that's 5 grid marks, right? So it's going to be over 1, 2, 3, 4, 5. You see how important that accuracy was there, right? Now I know which side this is on, and I'm going to sketch this really carefully. It's going to go down like this. And do I want points above or below that? Well, if I put the origin in, right, into here, I get 0 plus 0 is greater than or equal to 250, which is not true. So I want everything kind of above and to the right of the line. So I want this space here. Awesome. Now I know what points I need to find. So I need this point here, this point, and this point. Well, that bottom left, the last one I just did, that one we already found. Right? We just found that that's 25, 0. kind of going around counterclockwise here, this next point must be 35, comma 0. The point above it is going to be 35, comma 15. Okay, and how about that other point? Well, look, I know that the r coordinate of this point, because it's on this line here, the r coordinate of that point is 15. So this is something, comma 15. All right, good. So let's go to our equation here that we used to make that line. I'm going to put 15 in there. 6 times 15 plus 10c equals 250. 6 times 15 is 90, right? So if we move that over, 10c equals 250 minus 90. That's, oh, I'm drawing a blank. Sorry, 16, 160. So c is equal to 16. And I feel good about that, right? It's to the left of this point here, which was 25. And if you look at the scale, this is 5, 10, 15, and it's a little further over than that. So give her, there's always some inherent inaccuracy in diagrams, but yeah, I'm feeling good about that, right? That feels good as the coordinate of that point. Okay. So now if you think back to our procedure right from the last lecture, we've graphed the system of inequalities. We found the coordinates of the corner. So we've done step 1 and step 2. Now we just need to take these 4 numbers and put them back into the objective function, the cost function, and see which one is smallest. So now we're ready to answer our question. I've copied our 4 corner point coordinates into the first column here. And again, notice what I did. I'm still being super particular about making sure I keep the C and the R straight, right? So I actually wrote it in here. So I know that the first coordinate is the C and the second coordinate is the R. Then over here on the right-hand side, now I've brought back our objective function, our cost function. So to answer the question, all that's left is to stick these numbers into the formula here. For the first row, for example, C equals 28 times 15, right? That's the second coordinate, plus 52 times 16, which is 1,228, and these are dollars. And if you do this for the other 3, you get 2,240, and here you get 1,300. And do you see that we really don't even need the next one, right? Because this number is positive and this number is greater than this one, we really kind of know already that this one is going to be higher, and so it's going to be a loser. So, but I calculated it anyway. This is 1,820. Now we can answer the question. Right, we're looking over here. The row that has the smallest value is this one. Not by much, right? This one was actually pretty close, but that one does beat it out. So that is the answer to my question. Remember, as anytime you're doing this kind of word problem, practical problem, at the very end you need to specifically state what your answer is. So I would say she needs 15 rectangular tables and 16 round, I'm going back to the language of the original question now, 16 round tables.